Ayse Turak joins us from McMaster, and she's in the Department of Engineering Physics, and her research focus is related to interfacial engineering between contacts and organic materials for the purpose of semiconductor devices. To give you a bit of background about her, she did her PhD at University of Toronto, advised by Dr. Liu, where she worked on OLEDs. Following that, she was a Marie Curie Fellow at the Max Planck Institute for Advanced Materials.
Metals research.
Metals research. Okay.
I know, organic still, but metals.
Interesting. That's a good marrying of the two.
Yes, that's true.
So, and then she joined McMaster in 2012, so she's going to be presenting her research again on interfacial engineering between, her contacts and using nanoparticles to change those properties. So,
great.
I'm looking forward to your talk.
Okay, thanks very much, Irene, for that introduction, and thank you very much for inviting me here. I'm excited to be here. It's always very nice to come up the road and see everybody working on things close by. And in fact, one of my master's students came here to do a PhD, so I'm always happy to see her, see some of her work actually, so I can embarrass her while she's sitting there. So today my topic is on solution process nanoparticles for interfacial engineering. I thought that since this was a nanotechnology institute that I would focus on the most nano portion of it, though technically all of the sort of organic devices that we're talking about are always on the kind of nanoscale in terms of the thin films that we make. But my research is really focused on trying to introduce nanostructures at interfaces to try to optimize the properties, especially with relation to the performance and the stability. So just a brief sort of intro about those who may not have heard so much or aren't so familiar with the organic world of semiconductors. When we talk about sort of optoelectronic devices based on organic semiconductors, we're talking about the same kind of structures that you would see for inorganic semiconductor materials, both in the kind of transistor type structure and a diode type structure. And in fact, a wide variety of products have sort of come to market or close to market or around in the last sort of 20 or so years or 30 years since the first introduction of really viable organic devices. These include things like flat panel displays, flexible displays, RFID chips, sensors, wearable kind of displays, solid state lighting, and sort of my interest in the last couple of years is on organic photovoltaic devices. But all of these kinds of structures already exist or are out there in the world. If anybody has, for example, a Galaxy Tab or a Samsung Galaxy notebook or a smartphone, we already have OLEDs integrated into that screen. LG has an OLED TV, for example, that's out on the market. So these things, from when I started my first PhD, when I first started my PhD with Dr. Liu at University of Toronto, it was still quite a ways away that we would have sort of roll up the rim to win kind of thing where you could actually win an OLED TV. So in the last sort of 10 or 15 years, there's been a huge sort of movement forward, really drawn by the fact that all of these things are possible using these kind of plastic devices. So what's really interesting about OPVs in particular is something that we always call the unification challenge, which there are sort of three pillars upon which we want to introduce something new, a new technology, but in particular photovoltaic type technologies, which is really around how good they are, how much they cost, how flexible they are, versus their stability and their efficiencies. And the unification challenge comes from the fact that the three sort of points of this triangle are occupied by different types of materials. So things that are stable and efficient, which is most inorganic photovoltaic technologies that you might be familiar with, the solar panels on your house, they work really well, they're really stable, you can put them on there for 25 years, everything's great, but they're silicon, so they're kind of expensive, and they're not very flexible, so they're quite brittle, they have those kind of problems. Organic PVs technically could fulfill that niche, but when it comes to the stability and efficiency, they're still have a ways to go, I would say, in terms of their ability to penetrate the market. So the real unification challenge for OPVs, or perovskites as those things are coming up now actually, is to really look at processing stability and efficiency and try to find that sort of sweet spot where they come together. And my view, of course, is that the most important aspect of that are the interfaces that exist in these systems and how we can tune them to try to find that sort of sweet spot. So just as again, a brief reminder of what a solar cell is. If we think about what's happening in a solar cell, basically we take light, when a semiconductor absorbs light, these photoactive type semiconductors, they turn light into charge carriers, right? You have an excitation due to the sort of input of energy. Those charge carriers move to the electrodes, and then when they reach the electrodes, they're extracted to the external circuit, right? So you basically get some kind of input in of light, you form charge carriers, they're exposed to the outside world, you can use them to charge your battery, right? Like that's the whole idea behind how a solar cell works. When we talk about organic solar cells, they work in a very similar way, right? So we have light absorption, and but once we actually absorb light in these kinds of systems, rather than forming free electrons and holes, we have what's called a bound electron-hole pair, which we refer to as an exciton. So rather than having these sort of free electrons that we can do with whatever we want, we actually have an intermediate step where those electrons are bound together due to the weak intermolecular interactions between organic molecules that sort of confines the charge carriers to one location. So in order to actually form any kind of free charge carriers to extract electricity to be used for that battery charging, for example, you need to have some kind of interface, right? And these interfaces can exist in a variety of locations. Between the most common one you want to use is between a donor material and an acceptor material, so an N-type material, a P-type material, these kind of semiconductor junction type materials, or in fact at various electrodes. So all of these interfaces are necessary for the actual final extraction of charge carriers out of the system. So when we look at an OPV, the steps go, so here's a standard sort of structure. We have some kind of transparent electrode, substrate, upon which we have some kind of electrode, something that's a high charge carrier. The organic layers in between, split up into various types of functions, and then a top electrode at the top. So once we have light in, right, the efficiency is driven by the ability to form, for example, excitons. So how many excitons are formed when we shine light onto the surface. It's related to how fast or how far these excitons can diffuse or have to diffuse before they find some kind of interface, before they can separate into free carriers, which is driven by the energetics of those materials. Then once they've separated, they have to find their way to the electrodes. And once they're at the electrodes, they have to actually come out of the system to be used as free carriers, right? So there's a wide variety of properties or processes that are occurring in order for there to be that light to electron sort of transition. So in my group, at McMaster, what we do basically, so here's my little device. You can see that we have different kinds of interfaces. What we're interested in is tailoring the organic or the inorganic interfaces to try to boost the performance. So we're affecting all of those various types of properties of those different processes by looking at all the way from one-dimensional all the way to sort of full film device structures to see what we can do to tailor that performance. So overall, when we talk about interfacial engineering, as I said, we can focus on all three of the major interfaces. So the research that I do looks at the top contact, is very interested in what happens in terms of its decay properties, how it's destroyed at this interface, how that limits the ability of these devices to be used in the real world. At the sort of organic interface, we're very interested in how can we encourage these two materials to phase separate so that we can have a donor and acceptors mixed together in a meaningful sort of way to get extracted charges. And then finally, at the bottom contact, this is the one that's the focus of my talk today, we try to use nanoparticle electrodes that we produce by solution processing to, again, tune the various properties, the work function, the energetics, the morphology of those surfaces. So the focus, as I said today, is really on that last one. So looking at the bottom contact and looking at how we can introduce nanoparticles at that surface to really boost efficiencies and stability. So the way that we do it, and unfortunately this picture is very light, and I'm not sure if you can actually see it. I don't know if you can, maybe you can sort of see it. I apologize for the darkness. Basically what we start with is a diblock copolymer. So this is a polymer that has one hydrophilic and one hydrophobic end. And there's a little very weak looking, you can barely see it, container right here, excuse me, that we deposit in solution. So we put this polymer material into a beaker of some kind. And if you add enough of this material above what's called the critical Micelle concentration, because you have a hydrophilic and a hydrophobic end, they will spontaneously form sort of micelles. And when we say micelles, you can sort of see this picture here where all the yellow parts are on the inside and there's like gray on the outside. It's kind of a spherical shell material where the inside is hydrophilic and the outside is hydrophobic. And we start with this idea of having amphiphilic unimers. So again, what I mean by that is we take parts of a polymer that have these two properties as hydrophilic and hydrophobic end. And in this case, for most of our materials, we use a polystyrene polyvinylene mix. And the polystyrene is on the outside and the polyvinylene is on the inside that can react with other materials. And above this, what's called the critical micelle concentration, you get the formation of these spherical vesicles. And basically, if you have a polar solvent, right, a polar solvent will cause all of the hydrophilic ends to be on the outside and all the hydrophobic ends to be on the inside. And these are what are typically referred to as spherical micelles. And if you have a nonpolar solvent, you have instead a hydrophilic portion on the inside and hydrophobic on the outside, and we have what are called reverse micelles, right? So you can form either form depending on what kind of reactions you want to take. We mostly focus on the reverse micelle because we're interested in using solution chemistry to make materials that we can then sort of control the size of using these vesicles, basically. So the way it works in our particular system is making these reverse micelles. The inside, remember now, is hydrophilic. We'd add some kind of salt that is that's quite soluble in water or some kind of hydrophilic environment, but doesn't want to be in the nonpolar solvent that surrounds it. And so it'll infiltrate the inside of the micelle and form inside the micelle. Then we would add some kind of reducing agent so that we have a reaction occurring inside the micelle. And lo and behold, we form all sorts of interesting materials. So there's three principal reaction types that can occur when you add some kind of salt and a reducing agent. There can be precipitation by double decomposition. So these are both reagents reacting with each other. You can have just pure reduction, or you can have a hydrolysis condensation type reaction. So this allows, for example, the formation of different kinds of hydroxides or oxides or, in fact, halide type structures. So you can have a wide variety of materials that you can make metals, semiconductors, or metal oxide. So people have used this approach in a wide variety of areas to make various kinds of structures. In our lab, we've mostly focused on metal oxides. This is what we're mostly interested in. I'll talk a little bit about our ITO, or most likely a little bit of indium and tin oxide, actually. Some zinc, we've made titanium, we're making iron oxide quite recently. We also are interested in some dielectric halides. We've made lithium fluoride and magnesium fluorides in our lab, and a couple of metals. So we don't typically focus on them, but it has been shown, and we've shown a couple of places that you make gold or platinum through the reduction of the outside oxide. So typically what you would do is form an oxide first and then use some kind of plasma to reduce the oxide to its metallic state. So this kind of approach, the reason that we're interested in looking at it is so we can incorporate lots of different structures with about the same size into our devices, for example. And there's a couple of references for where we actually did that. Once we've actually produced the nanoparticles inside the micelle, the next thing, of course, is to get it into the structure. And what we typically do is just spin coat it or drop cast it or any kind of solution deposition approach onto our electrodes. And then after drying, we would etch them with some kind of oxygen plasma. And this would allow us to then expose a final, nicely ordered array of nanoparticles of fairly uniform size. And here's an example of such a system. So this is lithium fluoride that we started with. Here is a picture of lithium fluoride crystals coming out of solution without the micelles. So if you just mix the precursors together, you get nicely cubic lithium fluoride as you'd expect. But as soon as you start to use the micelles, you get nicely ordered, you get a nice array of nanoparticles that have a very small polydispersity index. So the variation in the diameter of these nanoparticles is quite small, on the order of about 2%, and we're looking at nanoparticles that are around 25 nanometers. And you can change the size of the nanoparticles by a variety of approaches. The easiest, of course, would be to change the size of the micelle so you get a larger or smaller particle based on how much room is available for reaction on the inside. So one of the first things that we did when we made these particles is incorporate them into solar cells, and this is what sort of has driven my interest in the last couple of years, is trying to understand what happens. And what we see is as soon as we actually introduce them into the micelle, into the the solar cell devices, this is an IV type curve, right? So we're applying voltage and we're seeing the current, and the short circuit current is proportional to, for example, the amount of light that you put into the system, or the absorption of that material. So what we see is that if we have our standard device, it's kind of terrible. Adding nanoparticles to the device increases initially the short circuit current quite substantially, meaning that we got more absorption of light, but we lose a little bit in terms of the properties. And so what we ultimately did, we found the best performance if we have both our nanoparticles plus another extra layer that Irene is very familiar with, and many people who work in solar cells is familiar with, a not so attractive layer called P.PSS that we're always trying to replace. But we found that if we can use both of these things together, we get relatively high performing solar cells with about a 6 times increase in the power conversion efficiency for these kinds of systems. So it's simply by introducing these nanoparticles at the surface, we're able to see a boost in the properties of these systems. Now, another approach that we wanted to take is to understand whether it was the lithium fluoride that was actually causing this interaction, or if it was sort of some other factor, for example, by putting a roughness into the system by having these nanoparticles. And so we wanted to try to make our own ITO nanoparticles and see if we had the same effect. And we were only so successful in making the ITO, so I don't have any device results to mention, but I'll just mention a little bit about the process that we took to make ITO. But we started again with the same kind of precursor and mixed together. We took 2 routes to see what would happen if we could actually use them the way that I just described, which is sort of as a nanoreactor, where all the micelle is really doing is giving a tiny little vessel within which you're doing regular chemistry that you would have done in a large beaker. So we just have a bunch of nano beakers, basically. And the other option, of course, is that it could, if we made ITO beforehand, if we could put them inside the micelles, then we could use that as a way of controlling the dispersion on the surface without too much trouble. What we discovered is that it is really this route, the nanoreactor route, that is successful in actually making in making nanoparticles, pardon me. And then once we did both of those routes, we would spin coat them on the surface and etch them to get the nanoparticles, which apparently you can't see. I think they're very, very blue, so you can't quite see them. So the idea is to have nanoparticles of ITO on ITO surfaces to see its impact in the device. And what we discovered, I'm just going to skip some chemistry here, sorry, is that basically if we used them as a nanoreactor, we were able to get lots of particles, and the particles were slightly smaller than our previous experience, slightly closer together, and slightly less uniform in terms of their size distribution, but still quite good, compared to having no particles if we made if we sort of mix the precursors outside of the micelles and then tried to infiltrate them inside the micelle. So one of the things that's important to know about making, well, I'll just skip this for a second, about making nanoparticles is the quality, right? So if we have nanoparticles dispersed on the surface, you can see an image of, for example, our lithium fluoride nanoparticles versus the first attempt to just drop these ITO-type nanoparticles on the surface. There's a big difference in terms of the number of particles, how dispersed they are, their kind of organization. And so one of the things that we're very interested in looking at and understanding, to understand how they perform inside the device, is how do we describe this distribution? How do we talk about what's best? What's the best configuration of nanoparticles? And this led us in a way to look at how do we describe the quality of nanoparticles. So here is an example where we have our optimized, from our perspective, parameters where we have nicely dispersed nanoparticles with space in between them. They have a particular diameter. The distribution of the polydispersity index of the diameters is quite small versus our unoptimized kind of rough system, right? And there's a wide variety of factors that contribute to this quality. So you can tune all sorts of different behaviors to sort of combine those two kinds of structures. And these things include things like the choice of the solvent. So if we use toluene versus some other solvent, like oxoxylene, for example. Here's an example from literature where people have actually seen a substantial difference in terms of the size and sort of quality of the distribution of particles. It's also affected by things like the purity of the precursors or the purity of the polymers that you use. If you use sort of not totally optimized or clean materials versus ones that have been sort of cleaned in some way. So here's an example of non-fritted. Here means that we didn't process the polymer material to remove it of oxidation, and fritted we had done so, and you can see again, sort of visually, you can appreciate hopefully the quality difference that occurs in these systems. And things like post-processing. So if we apply other kinds of annealing effects, if we heat it up, for example, or we try to use a very standard technique called solvent annealing, when you expose it to a solvent over a long time and not let it evaporate quickly, this allows the polymer materials to sort of reorganize themselves on the surface. And then even things like the volume of material you use or the spin coating parameters, the speed, all of these things can affect ultimately the dispersion, right? And since it's really nice to look at pictures, you can sort of appreciate that there may be a difference between these two, but ultimately we wanted some way of actually being able to classify these structures to say, well, which one is optimized? When we say the word optimized, what are we really aiming for, or what do we think is going to be the best? So we spent a lot of time trying to understand and quantify quality. And so our idea, of course, is not limited only to our nanoparticles. Here's an SEM image of a nanoparticle surface, but can also be applied to different kinds of structures, including mixtures, for example, of organic molecules that have a particular shape. So we're very interested in how can we differentiate between something that is maybe very ordered or more so ordered than this one, which is very disordered, right? So if we're going to classify structure and dispersion, the question is really, can we say with some kind of metric or some kind of qualitative value the difference between this and this, right? So when we look at them, we can appreciate that there is a clear difference between them. So how do we actually find a measure of how good they are or how close together they are in terms of their properties? So if we look at order, so some of you may have seen or been appreciate the idea of an ordered lattice, right? So we talk about single crystals where things are very periodic. We see like lots of regularity in terms of the positions of particles in this case, or atoms or anything. And you can have also, it's very clear to see, what's called complete spatial randomness. This is a situation where there's no relationship between particles, and you basically have a random distribution of particles positions relative to one another. But in between, there's a whole slew of what we'd call regular patterns. So these are patterns that have some kind of order, maybe short-range order, that we'd want to be able to classify between these two structures, right? This is easy to understand. This is relatively easy to understand. What's happening on the inside is what we care about. How can we quantify that to find, again, this idea of an optimized parameter set? So in our group, we've taken three approaches. Something called Voronoi tessellations, which I'll talk about in a second. A pairwise separation, so the distances between various particles, and something called the bond order, which I'll also reference towards the end. Right, so we're going to look at each of these in turn as ways to classify structure. So the first one is just a Voronoi analysis, and the idea behind Voronoi analyses is just to basically look at your neighbors, basically. How many neighbors do you have? How far away are they from you? And all you do is you draw a line to each of your neighbors. You create a perpendicular bisector, and then you do this all the way around your centroid particle, and then you get a Voronoi cell, what's called a Voronoi cell. Okay? So the intersections of all these sort of bisectors define some kind of cell. So if you look at a random distribution, or not random in this case, but a regular distribution of dots, you can actually see different particles have different shapes for each of these different cells, these Voronoi type cells. And one thing that we can do is classify it against, say, a hexagonal lattice. So a hexagonal lattice is one that has perfect order, perfect separations that are well understood. And you can compare the number of these particles that have shapes that are similar to, or areas that are similar to what we'd expect if we had a perfectly hexagonal lattice. So here is a map, for example, in the heat map here shows you that blue means that it's closer to being perfectly hexagonal, and red means that it's very far away from being hexagonal. And you can even go one step further and then classify each of how far they deviate from that expected Voronoi kind of cell area. This kind of an approach allows us to easily see the difference between, for example, a perfectly hexagonal system. So you can see here, perfectly hexagonal, totally blue, right? Are totally random, completely independent, no relationship to each other, lots of red. And then our regular patterns are somewhere in between, right? And so because we can look at the relative numbers, and in fact, you can also use this in percentage rather than in the sort of count numbers, you can extract how ordered something is based on how much you see in this kind of region versus how much you see in this region, right? So our blue ones are very ordered, red ones are totally disordered, in between we have something else, right? So one way you can apply that, and we have applied it, is to look at, for example, the deposition of these nanoparticles on different surfaces, right? And you can look at all of these and sort of try to appreciate them just from a visual perspective, but it's hard to say whether one is better than the other or different than others, that kind of thing. But you can easily, using this kind of tool, you can extract all of these different areas and get a quantitative value of how close these systems are, right? And so you can see in this case, it tells us that the amount that are really close to being hexagonally close packed is very similar in different cases, but the silicon nitride surface, for example, has much less of the really disordered systems. And so we can say with some level of assurance, I guess, that this silicon nitride is more ordered, or is closer to an ordered system than our ITO surface, where it's slightly more disordered, right? So this is a way of us trying to classify which of these surfaces is going to optimize our parameters, right? This is the idea. So this is one way that you can apply such an approach to classifying order. On the other hand, instead of looking at these Voronoi areas and how you expect them to look relative to their neighbors, you can use other kinds of metrics, right? So we're looking at lots of different metrics together to sort of classify something as being ordered or disordered. And another way is to look at the number of neighbors. So when we talk about coordination, we're talking about the number of nearest neighbors. So in the case of a hexagonal lattice, again, you'd expect there to be 6. Here's our hexagonal lattice. They're all there. Here's our disordered system. We have a huge distribution. Our better ordered system, our more regular lattice, has a slightly smaller distribution of coordinations, right? Lots of 6s, lots of other things. And the reason that one might be interested in this rather than something else, I can just use this as an example. Here's a system that this is a simulated system, obviously. We're dynamically adding particles to this corner. And you can see that, that there is some kind of order here. And in fact, there are 2 overlaid lattices. But as we add particles, if you rely only on the areas, it looks like the whole lattice is getting worse, right? So these up here go from being perfectly hexagonal to all of a sudden not so hexagonal. But if you look at it from a coordination number perspective, you see that all of the addition is happening in this corner and nothing is happening at the top, for example, right? So this area is not actually changing, but if you rely on the sort of the expectation areas, you can get sort of widely varying ideas of what's order or what's disorder in these systems. Right? So looking at multiple parameters helps us to really understand our systems much better. So that was a Voronoi type of approach. So we look at different kinds of positions and their areas and how they're ordered relative to each other. But you can also look at sort of the nearest neighbor distances, or distances between all of the different pairs of particles. So for example, if we take particle 12 here, you would calculate all these differences and then add them together into a probability distribution. And from that, you can extract, some of you may have seen this kind of thing called a G of R type spectrum, where again, for a hexagonal lattice, it's very well known what it looks like, and so you can appreciate the difference between our data set, whatever it is, which is in green here, versus what we'd expect if we had a perfectly hexagonal lattice, right? So this is another way of looking at data. If any of you have ever done any kind of XRD type measurements on your samples, the G of R is basically a very similar description to what you would get, this 2 theta spectrum. Right? It has to do with the distances between neighbors. And this distance description, of course, is again related to the positions and the areas of these various kinds of these Voronoi areas, because each of the peaks corresponds to, for example, the first set of neighbors, the second neighbors, the third neighbor shell, the fourth, et cetera, et cetera. So it tells you about both short distance, so close, how ordered it is in the close range, but also how ordered it is on a long scale, right? So you can actually extract both short range and long range order by looking at one system with one sort of cumulative distribution function. And if we look at that again so here are our three very ordered, not totally random, sort of regular patterns. And you can see the sort of evolution of the structure from being almost, this is exact, right? So we're comparing it against the hexagonal lattice versus some difference versus the hexagonal lattice, but the positions are very similar versus no kind of structure that we can reasonably say exists in these systems, right? So using the pair correlation function also allows you to sort of appreciate the kinds of order, short range and long range, that exists in this system. And one way that we would use this, so here's an example again of the quality of our nanoparticle dispersion that we might be interested in. For example, how well ordered this 4 microliters is versus 13 microliters, right? So which one of these is optimal or the best ordered structure for our purposes, right? And again, just looking at them by eye, it's very hard to get a feel for which one is better than the other, right? And we can use, instead in this case, though we could also use the Voronoi cells, we can use these pair correlation functions to really see that in the case of our 4 microliter, the green sort of follows this purple values much better than, say, the 12 or 13 microliters, where you see very little structure relative to this one. Right? So you have, again, a quantitative comparison between this structure and this one to make some kind of metric, and you can take, for example, the difference in the spectra from hexagonal to tell us which one is the best. Right? So again, this idea of optimizing the parameters depends on what you're interested in, but if you're interested in really high order or relatively high order, this structure is better than that structure. Right? And you can have a quantitative way of describing that, which you can't immediately extract by looking at the images directly. The only interesting thing, of course, about these pair correlation functions, though they're very powerful, slight fluctuations can lead to apparent loss of order completely. So what I have here is a little animation of slight fluctuations in the lattice from the expected positions of the hexagonal lattice, but when you look at it globally, it looks pretty hexagonal, right? It looks roughly like nothing has really changed when you look at it by eye, but from the pair correlation function perspective, you go from having very nice peaks to having huge differences from the expectation values, right? So this kind of behavior means that it's hard after a little bit of wiggling to distinguish between a really ordered system and one that just happens to be closely ordered, but the positions have some kind of error in them. And as we know, if we're doing any kind of experimental work in an SEM, there is always a parallax kind of problem, or AFM, for example, where you don't have, you can have slight errors in the diameters that you're measuring or the exact positions that you're extracting. Where is the centroid of a nanoparticle that we're going to use for this purpose can have a huge impact on how ordered it seems according to these kinds of parameters. So we can take this into account by describing a different kind of lattice. So instead of going for purely hexagonal, we can go for something called a hexatic lattice, where we have some broadening happening in these systems. And we can then appreciate the difference between different structures by looking at how hexatic they are, or how much this broadening has needed to be done in order to see that kind of structure. And again, you can see here that it doesn't take very much before it becomes quite distorted from our original hexagonal lattice. And again, we can use this to look at our three surfaces and establish some kind of understanding of their quality by looking at how well they match, for example, a hexatic lattice that has slight deviations in its positions. And again, we can see from this case that that our various structures might give us better or worse descriptions of order, right? So our Voronoi cells told us that maybe the silicon nitride was the best. This one suggests that ITO is slightly better in terms of a hexatic kind of phase, right? So these approaches all allow us to define for our particular systems which one is going to fit, or we understand better the distribution of these particles on the surface. And you might ask, oh, what happens then if we have this hexatic phase? Well, another way that we can describe it is through something called the bond order, which is basically, instead of having our neighboring particles that exist, we just join them all together with various kinds of bonds. All right, so here's our green particles are all bonded to this pink one, for example. And then we can use the angles between these bonds to describe the system in general. And so you can, for example, compare this against a traditional hexagonal lattice to tell us, well, how close is it to being perfectly hexagonal, right? In a hexagonal system where everything is ordered, the angle between 2 points should also be fixed, basically. If the distances are fixed, the angle is also fixed. So we can also use this to classify our systems and distinguish between perfectly ordered systems to ones that are not so ordered. And this description of the hexatic phase is really based on ones that have a lot of order, even though the positions might be off. Right? So we can use all these different types of classifications to tell us something about the nature of these dispersions on the surface. And so the question, of course, is why would we care? And well, part of the reason is that we, in addition to being able to tune the parameters, as we talked about for these nanoparticles, we can also tune the coverage of nanoparticles by, for example, changing the number of times that we deposit the nanoparticles, or we change the nature of the solvent. We mix two solvents together, you have different dispersions. And you can do things like, for example, if you have sort of some particles that are left over when you plasma etch, you can do a second run and fill in those particles. So for example, going from lowish coverage or medium coverage to some slightly higher coverage by coating the surface multiple times. And this has also been shown to have an effect in solar cells, similarly, where there's an optimal value of coverage that gives us the best kind of performance. So the reason that we care about how these particles are dispersed in these systems is to really try to pinpoint what is happening in this structure. Why can we see particular amounts of coverage really give us the perfect sort of, or not perfect, but the improved device performance that we're seeking, right? So that was most of my time anyway, so that's really just a quick sort of highlight of what we've been working on or what we're interested in terms of tuning the properties, right? The idea is to link these ideas of, for example, bond order classifications to the performance that we're seeing coming out of real device structures. That's really the ultimate goal of this aspect of my research. So just to sum up, this technique, the reverse Micelle deposition technique, where we basically have vesicles that act as little reactors, where we can control what's happening on the inside just by using very simple solution chemistry. We just mix two materials together the same way you would in a beaker, but rather than using the whole beaker, we just use the inside of these little micelles, is a really powerful tool that allows us to have very, very narrow particle distribution sizes, right? So we can get lots of particles that are all roughly the same size, driven by the size of the micelles. And though I didn't talk about this too much, because we expose it to a plasma, you actually clean off all the crap and the dirt and the toluene and like everything that comes onto the surface. And if you combine that with, say, an electrode surface like ITO, which also needs to have that kind of exposure to clean it up in the first place, you kind of are killing two birds with one stone, which helps a lot if you're thinking about it from a manufacturing perspective. You can sort of save a couple of manufacturing steps. And because we don't go to high temperatures, it takes relatively low energy, right? We are allowing nature to tell us what are the reactions that are going to occur. We add enough reactants so that they come together. We just remove the micelle, and lo and behold, we're left with nanoparticles, right? So it's very low energy system. These nanostructures have been shown to have these sort of very significant impacts on the surface, and one of the things that we're interested in is understanding what is causing those impacts. What is it really sort of driven by? And I didn't talk too much about the electrical properties, but these materials, some of them are semiconducting oxides, but some of them are wide bandgap insulators. And so the difference in different material sets gives us an interesting insight into what's really happening at these surfaces. Why are we getting such performance improvements, for example? And then finally, because we can control them with the dispersion or with various other types of parameters, we can generally tune the surface to give us these optimized coverages, right? And when we talk about optimized coverages, we want to then tie it back to, well, what does that really mean for the order or disorder of that system, right? There's some controversy, for example, of whether a really ordered nanostructure array is better for a solar cell than one that's completely disordered, for example. So we can look at those kinds of structures by understanding how our systems are dispersed, so that when we see the optimal sort of performance, we can gain some insight. And I just want to thank now the students who've been involved in this work, and and you can see here's Christina, so she did some of that ITO work from earlier. We have some students who are involved in sort of producing different kinds of nanoparticles, and a lot of the work that I showed at the end of these order classifications is from my PhD student Mike, who really developed a beautiful little Mathematica notebook that if you just put in the positions of the particles, you can get all of those beautiful pictures that I extracted immediately just by clicking through the notebook, and it'll do it automatically as long as you have the centroids. You can get all of the parameters basically with one click, which is really nice. And I think we're in the process of putting it up on our website, so it's going to be freely available as soon as we write that paper, really. But that's what it comes down to. But it's the kind of tool that will allow you, as long as you know what the centroids are, you can basically extract all the parameters you're interested in. Which is great. And then, of course, we're also interested in other things about these micelles, their electronic properties, their mechanical properties, and so I have a number of students working in that as well. So without the students, nothing would happen, so I'm glad that you guys were here to come and see this. I'll just do the obligatory thanks to my collaborators and thanks to the funding agencies, and really thanks to you for coming and listening, and I open the floor for questions. All right, so thanks very much.
So sorry if I missed this, but can you just clarify the role of the nanoparticles in the improved short circuit?
In actually improving stuff?
In the cells, is it
so
morphology or optical?
We think that it's related partly to the work function, because we did some, I didn't show this work, but I think I have it over here. Let me just skip to that portion. So here's our basic device. And what we saw, we looked at a variety of things to try to pinpoint what's the actual driving force. And it definitely has to do with the contact in some way. So if we look at the dark device, for example, we see that we see our improvements here in the surface resistance. So when we have the nanoparticles there, the series resistance at the surface seems to go down. So we're able to we were sort of interested in where that came from, and we can sort of think about it being related to the bulk resistance of the contacts or the bulk resistance of the films. I know you can't see it at the bottom there. What was it? Sorry. Oh, I don't know. Anyway, we have various kinds of possibilities for why these particular surfaces are so right. So this is the bulk resistance or the actual contact resistance itself, right? And so when we look at the various properties of these surfaces, the one that's the most important, it seems like, is the work function. And we see a tunable work function as a function of coverage. So these are actually just work function maps. And we see that when we add the nanoparticles on the surface, it has a very similar effect to if we just oxygen plasma etch the surface, for example. But we also see an interesting effect in terms of the bulk resistance of the polymer, that if we don't have the P-dot PSS layer, we do have some, basically we have some kind of traps that are existing in these systems. And so we mostly are attributing it to this contact kind of a behavior. And and I'll just show you, I think I had hidden it here, but there's sort of three different things that we think are occurring in these systems, and that potentially could be occurring in these systems. It could be optical, it could be electric. Let me just show this here. But one of the first things that we have seen, if this ever comes back, there we go, is that you can actually tune the work function as a function of the coverage, right? So the number of nanoparticles that we have on the surface does seem to have an impact on the measured change in the work function of the ITO. So this is most likely one of the predominant effects. But one of the things that I'm very interested in is it just the pure number of particles, or does it have to do with these sort of dispersions? That's why we're very interested in looking at how ordered they are on the surface, right? Because this effect, sorry, so this just tells you about something about the border. But there's, of course, other kinds of effects that can exist in these systems. The most common one I would think of is having nanoparticles, for example, here that are ITO. We can have a tunable or change in the electric field just surrounding the contact. by the sheer nature of having defects at the surface of ITO. And we have seen that when you have that kind of tunable roughness, that you can tune the molecular orientation of the molecule. So this is going into a little bit more detail than I'd planned on, but you can have different kinds of configurations. And we have seen that, that typically people believe that this kind of a face-on configuration is much better to allow for injection than this kind of structure. And we imagine, and you can't really, unfortunately, you can't see it, but imagine that these are blue nanoparticles here. When you have the molecules depositing on the surface, you're more likely to have areas of high injection right around where the nanoparticles, around the nanoparticle edges where you have approximately a face-on type orientation, right? So we think it's a combination of these things, and in fact, we've seen some evidence. This is not actually in nanoparticle roughened systems, but in a regularly roughened system, we have seen quite a large improvement in the device performance as a function of how rough that surface is, for example. And then the second one, as you rightly mentioned, has to do with the optical field. And we've been doing, oh, can't see any of the blue layers, but anyway, in the idea that if you have planar interfaces that are quite flat, you can have all these waveguiding modes that these nanoparticles could disrupt. Right? So these are various things that we're exploring. We've definitely seen this work function effect, but these other effects, which are related really to the spacing and the dispersion, we're still exploring them. Yeah. But thanks for asking that question. Then I got to show all my extra slides. Any other questions? Yeah.
So you mentioned that your optimal efficiency was for a specific coverage percentage.
Mm-hmm.
But maybe I missed this, but is that related to a degree of order?
So it is related to the degree of order in the sense that that when we have less of the materials, they seem to be more disordered. And so one thing that we're very interested in is if we have similar number of particles but different types of order. That's sort of what we're trying to tune that area. Can we boost it even more or not? So this is something that is it's still work in progress, but that's sort of the idea, is that this optimal value, we definitely see that if you change the spacing between them, right, things are different because you have different nanoparticles. But the real question that's outstanding for us is if we have different nanoparticles, or we have, different number of nanoparticles, is it purely a number of due to the number of particles, or is it due to how they're arranged, right? Because the more particles you add, the closer they are together, the more disordered they are. The lower coverage ones are more ordered, basically. But, in a hand-waving sense, I'm saying those words. Right? So we want to really explore that in a meaningful way. But thanks for that question. Any other questions? Yeah.
Maybe just one more
Sure.
general one. So you've developed these really nice techniques for categorizing or quantifying, I guess,
Mm-hmm.
the degree of order, and you applied it to nanoparticles on the substrate.
Mm-hmm.
Do you have other sort of applications in mind, or do you see the same techniques could be used?
We do. Our biggest other technique is looking at supramolecular structures of organic molecules because they have shape. I showed a little sort of teaser of it in a way earlier on when I was just talking about what we can apply it to or what we care about. And here's an example of, so here's our nanoparticles that are just round, but here are sort of these happen to be fractal patterns, but our ultimate goal is to look at, for example, if we take the shape of our molecules, which actually have shape, they're not just round, and we mix them together with different molecules, the donor acceptor type molecules, can we classify the order of the two structures together, right? So we have, for example, I think I included some in here. We've been doing a lot of work looking at various mixtures of particles, and I think this is an example. We have a picture of it here. Sorry, this is one of my selling slides kind of thing. So this is another type of structure that we look at is looking at, let's say, mixing these two different molecules together. One of them happens to be an acceptor molecule, one is a donor molecule. And even when we have sort of two of them mixed together, we can still extract these parameters for each individually. That's the idea. And and we're very interested in, how can we tune the order of something by, for example, putting them under confinement, or how do we modify the organic molecules beyond just the nanoparticles themselves. So this is our other major interest. So this is where I didn't talk about, but we're also interested in organic interfaces, but mostly on this sort of molecule level scale. Yeah.
nanoparticles, I saw mainly the improvement was from the current.
From the short circuit current, yes, that seems to be mostly the way.
Meaning, like, it could be very interesting if you can show how much of reflection reduction there is, then you can say how much is from the optical side, how much is from the electrical side.
Exactly. So this is definitely something that we're looking at is extracting how much absorption we have. We have seen that when we have the nanoparticles on the surface itself, there doesn't seem to be too much of an impact on the absorption. And I believe, just one second. So we did, for example, look at the transmissivity properties of these systems, and they're almost identical to ITO when we put the nanoparticles on. And we haven't seen too much of a change as a change of the coverage, right? So we basically just see pure transmittance. So it doesn't seem like it's some kind of plasmonic effect or anything like that. There isn't a huge improvement in the absorption. But we do think that there might be some scattering effects that are occurring. So we definitely are trying to decouple the electronic and the, and the optical effects, partly by trying to make ITO, right? So that we can look at purely optical effects. Really, that's one of the driving forces for why we were looking at ITO in particular. But yeah, that's a great point. Yeah.
So what's the size range of the nanoparticle you can achieve with the reverse Micelle?
So typically the range can go from anywhere around 10 nanometers, but smaller is always harder, obviously, to about 40 nanometers. This is the general range. Above that size, the micelles themselves just become unwieldy, and you need a lot of micelles to form micellar vesicles. If you use different kinds of micelles than the ones that we use, you can form other kinds of structures like cylinders and squares and things like that. We focus on these really round ones, but that's roughly the range.
Have you looked at the size effect?
The size effect in terms of these devices?
Yeah.
So we haven't, because we haven't. But yes, these are all questions that we're very interested in exploring. Yeah.
I have a question. So
Yeah.
your devices, do you put PDOT-PSS?
Well, we did have to, yeah. So that was basically, we ended up doing 3 configurations. We did just PDOT-PSS to compare, then just the nanoparticles, and then the PDOT-PSS. And what we saw is that the short circuit current definitely is improved if we just add the nanoparticles, but we don't quite get the open circuit voltage. So there's probably some kind of recombination loss at the surface of the nanoparticles.
Why would changing the work function of ITO improve things if it's copper with PDOT-PSS?
See, so again, it all has to do with how well those things marry together. There is, if you change, I don't think I included it here, but the work function of ITO and PDOT don't match perfectly either. And so as you tune the coverage, you can actually sort of tune the position of the work function of the surface so that it matches perfectly with PDOT-PSS, in which case then you have good injection. But we don't. So the ideal work function, well, if you want to match with PDOT-PSS, would be to get basically 5.2. So it's exactly the same. The idea there is that you wouldn't have any barrier to injection, though technically if you go below that, it should also be pretty good. But as we were talking about earlier, the PDOT-PSS does something a little bit more than it's not just purely the work function matching that seems to be the effect. And because we lost in the open circuit voltage, that has a lot to do with the recombination locations, right? So where we have sort of exciton splitting. And if exciton splitting is happening at the surface of the nanoparticles, that's not so good compared to having it be between the donor acceptor molecule pair. So the PDOT-PSS seems to sort of prevent that kind of reaction. It could be that it's happening at the ITO surface because we don't have full coverage, right? So these are open questions in a way. Definitely. Lots of open questions. Always open questions about these systems. There's lots of things happening simultaneously. So thanks a lot for that. Yeah?
When you were talking with the Micelle
Mm-hmm.
kind of process, it very clearly looks like kind of something that could be formed by a phospholipid bilayer.
Yeah, it is a phospholipid bilayer of sorts. I mean, you could do the same thing with a phospholipid bilayer as long as you have an amphiphilic sort of structure.
Right. So my understanding was you were using some sort of polymer material.
Mm-hmm.
If you were to change that to something more organic, that significantly change your operational temperatures?
That's a good question. We generally do everything at room temperature, and so there's really there's no need to go to high temperatures to form these micelles. They just form spontaneously at above the critical micelle concentration. But basically any surfactant would do the same. It's all a matter of how stable the micelle is when you introduce these reactants. So a lot of materials, when they react with, when you sort of, let's say you put a salt into solution, if the salt infiltrates the phospholipid bilayer, often it will react with the bilayer components, and then the micelle will fall apart. The beauty of these diblock copolymers is that they have it's not quite a covalent bond interaction, so there's some kind of, probably a charge transfer interaction, relatively weak sort of chemiabsorption, and so they tend not to destroy the micelles when they infiltrate them. So the problem, of course, is having, once you've added the reactants, how do you get the micelle to stay in that until you want to take it away? So so people have tried with these phospholipid bilayers, but it's generally seen that with some of these materials, like if you add zinc acetate or indium acetate to the solution, the micelles just dissipate, basically, right? But it is quite versatile. As long as the micelle itself can maintain intact, you can really use anything, right? Any material that has this same property. Excellent question, though. Yeah?
So how do you measure the work function?
So we use a Kelvin probe, scanning Kelvin probe with a relatively large probe. So we have a 2 millimeter probe, but you could also do it at the at the sort of AFM level and look at individually what it looks like. We're interested in the global work function of say, a pixel. And that's why we use the scanning sort of two-dimensional method, because if you use something else like ultraviolet photoelectron spectroscopy, which is a very common way of measuring the work function, you will get the sort of the lowest work function of the surface and not the average overall. So that's why I showed those maps. I think did I show them here? No, I don't know. I don't know where they are. Come back to me. Right, so here's the maps that we sort of take of the surface, and then we get the overall average change, basically.
The reason I'm asking is if you measure the work function outside of the solar system, and then you have your solar cells that are the nanoparticles creating sort of a junction inside the cell.
Like specifically at certain locations?
It would be like an interface of several junctions on the same layer, as opposed to, so that would be different than just changing the work function.
So that's a very good point, and it's something that we're a little interested in, right? Are each of these nanoparticles blocking a contact, for example? So we use lithium fluoride. Lithium fluoride is a wide bandgap insulator, and so technically there should be no charge injection through any areas that have nanoparticles. We have not seen the development of say dark spots directly above those locations or anything like that, and so that we don't think that that's the case. But this is partly why we want to explore other material systems, because if it's purely due to that kind of an effect, where we have just a lot of contacts and they're separated by, in between the particles, let's say. So those areas between the particles where there's bare ITO, we have lots of charge injection, and on top of the nanoparticles we have none. Then if we change it to, say, ITO nanoparticles, we shouldn't see the same kind of behavior, right? That's sort of a driving force for that. And so we've looked at a couple of different material systems, and it seems like the effect does occur for lots of different nanoparticle types. And so we're still in the process of exploring all the different types of nanoparticles that we might be interested in here. But it seems like this global work function change seems to be due to the way that the nanoparticles themselves change the electron overspill density of the surface, rather than making individual sort of short circuit current like contacts. It seems to be this sort of global effect rather than localized. But excellent question.
Very good. Well, it's 4, so I think we should, if you have other questions, I'm sure Professor Turak
Absolutely.
happy to answer them after the talk, so let's
Great.
thank you very much.
Thanks very much.